Hello, guys. I am Gilberto Thomas. I am from Universidade, professor at Universidade Federal do Rio Grande do Sul in Brazil, and I'm very happy to be here to participate in this workshop again. Okay. Let me see. Here is the share screen. I'm going to talk today about, in this lecture, about continuing Julio's lectures about cell growth and cell division. Cell growth and cell divisions are properties and kind of behaviors that are implemented in CompuCell, and then they are very useful for the simulations we plan to do. The outline for this lecture here is this one. Here's the title, here's the, I think it's something is messed up here. Okay. I'm going to talk about cell cycle, then start with cell growth, cell division, and finally with some specific feature, which is contact inhibited growth. I mean, when the cells are maintaining with some pressure from the other cells in a tissue, for example. Okay, let's see. Cell properties and divisions, we can say that it is maybe one of the most important things to create multicellular organisms, because the cells have some internal programs, some blueprints internals that, and the cell must decide, continuously decide whether to proliferate, survive to be in a quiescent mode, for example, differentiate, or to die. Everything has a complicated route, metabolic rates for this process to occur, and involves growth factors, and as you can see from this picture aside. Okay, there is a lot of other things that will influence the cell growth and division, like the amount of nutrients in the environment, the pressure that the cells receive from other cells, if there is some contact with some immune system, for example. And it's a very complicated and very numerous ways to implement cell division, cell growth and cell division. But to start with, we have to say that when a cell decides to divide, to proliferate, it enters in the cell cycle. The cell cycle is a cycle composed by 4 stages, where the cell starts to produce some metabolic products like RNA and other proteins. They enter in a stage that the cell stops to do anything. This is a preparation for a DNA synthesis inside the nucleus, new production of proteins, and then the cell enters in a mitosis event, and then this starts all over again. So those are the steps that the cell presents when they decides to go in a division, to proliferate. Of course, to pass through each of those steps, those phases, G1, S, G2, and M that we just saw, there are some checkpoints that the cell has inside as a control to keep the machinery running smoothly. If something goes wrong, the cell dies. immediately, and entering apoptosis and die. Okay. Of course, this cell cycle with checkpoints is a very complicated mechanism. You are not going to model this in CompuCell3D right away, in details right away. Well, we hope someday we can really reproduce that thing in details. But so far, we want to analyze what we can grab from nature to bring to this CompuCell and start a simple model. Okay. For the cells, what we analyze? Well, we have cells, for example, in a petri dish. We analyze the space that the cells have available to grow and divide, how much nutrients they have, how fast they can absorb and the nutrients and increases their mass. If there are, for example, growth factors involved in the nutrients, if there are too many cells and substrate that could prevent the cells to move and proliferate, which state of the cell is to start the process, if there are some toxins that could prevent the cell to enter in the cell cycle, and lots of other things that we can analyze. But for us, the simplest model in CompuCell is say that we will have a cell, a single cell with no internal structure to start, and the cell will grow and will divide with according to simple rules that we are going to say here. For example, the easiest way to promote the growth is to say that target volume of the cell increase a constant rate at each Monte Carlo step. For example, I would say that here the volume target, it's equal to volume target plus a constant factor that you can decide how much it is. And we will say that when the cell has, for example, the double of its initial size, we will divide the cell. Okay, this is the simplest case. So these modifications in the growth, I mean the implementation of the growth, is made easy in the XML file when you write the simulation. We will see very soon, but for now, let me explain here. We have this plugin volume that is loaded in the XML file. And in the steppable, we will control the volume target and the rate of the growth of this volume target in the step function of the steppable. Okay, so we define the cell target as a constant at the beginning of the simulation, like in this line as 25. And in each Monte Carlo step, in the step function or the steppable, we increase this cell, the target volume by some amount, to say 1.01 size of a pixel, for example. Okay. Okay, let's do the first exercise to implement this easy cell growth in the CompuCell. Let's create a simulation where the domain is a two-dimensional 100 by 100 pixels. Initialize the single cell type called cell, for example. Let's use the usual contact energies that comes with CompuCell, and include the plugin volume local flex, because we want to change the target volume in the steppable file. So you cannot use the regular volume plugin. Okay, volume local flex is the plugin that allows you to change values in the Python steppable file. Okay, so let's see. Let's go to the NanoHub and build this simulation. Let's see if I can put this in both windows here. Here. Where is the... I have to... Oops, session quota exceeded. I have no idea what is this.
Just close one of your instances of CompuCell.
Inside the NanoHub?
You can only run 3 jobs at once. You have 3 jobs
okay.
open.
Here then.
No, in the window you were in before. Just say terminate. Select terminate in the middle. In the middle under my sessions, terminate the session. In the middle, down below, select terminate. Right? No, right where you are. There you go. That's something that's useful for everybody. If you have too many jobs open at once, it'll tell you that you can only have 3 jobs running simultaneously.
Gilberto, you're muted.
Why was I muted? I don't know. Okay, then you create, give it a name, and choose Python and XML. Then click next, that I cannot see where the next is here. And here you define the grid, 100, 101. Make this blob initializer here. and next, and create a cell type cell. It's complicated to see this. I didn't add cell. This very long. Next. There are no chemical fields present in the simulation. Let's skip it. And then we have to choose the behaviors and the features of the cell. So we are going to choose the contact, usual contact, volume local flex, surface local flex to begin, if you need later, and growth, and that's it. There are five properties being included in the simulation. Finish the simulation, and we have, now we can go to the CompuCell, which is here, and open this file. Oh, you can open here also. You can open in player here. Well, it starts automatically. I don't want to start because we didn't make any modification there. We have to do the following. We have to decide how many cells we want to build. Okay, so in the project, okay, we are going to modify the blob initializer part of the code. We have this part here in the blob initializer where we're going to write that we want only one cell, a single cell of radius 5 and width size 5 as well. So here in the, where is my, here, it misses all the time there. I'm crazy with this. Here in the blob initializer, which is in the XML file, here, we're going to change this to 5 and this to 5. Save it. Go back to the presentation. And in the steppable file, well, and let's see, in the steppable file, we are going to say that we want to change the growth rate to include this value of 25 voxels per 500 Monte Carlo steps. I mean, each Monte Carlo step, the growth of the cell will be a fraction of a voxel, okay? 1/20 of a voxel. Then let's include this there. We have to go in this file here, say that at this step function. $25 over 500. Save it. Now we can go to the stop and see, now we have a single cell centered in the grid. Okay, so if I put it to run, I don't know what happened. Let me see. Jesus. Okay, let me go back to the code here. What is cell target volume 25, cell lambda volume 3, 25. This is being a disgrace. Sorry, guys. Where is the editor? Here. Maybe this one. The energies. Oops. Let's see if the energies is. No, it's correct. Why is not working?
The lambda value, if you set to 3, it works. It kind of seems to work for me.
Ah, okay. Yeah, I just changed it now to 3. Thanks, guy. Where's CompuCell? Here. See, the cell is growing there. And I cannot change the size of the simulation. Yeah. Okay. So the cell starts with a size of 25 pixels, voxels, whatever. And with that growth rate, it starts to grow until occupies all the space of the grid, if you don't stop, if there is no stop condition, for example. Okay? So this is the easy way to make a cell grow. Now, we have to do the following. Let's change a little bit the simulation, including this cell, using the target surface and lambda surface plugin. Okay, we have to do this by including this in the simulation, in the code. Those lines here, we have to include this cell target surface 20 and cell lambda surface 3. also. This is too bad. Where is this? And then in the steppable, we're going to include here copy the surface, surface, surface is 20, and we are going to save the simulation and run it again. See, this the plugin was already loaded in the XML file from the beginning. Okay, the plugin volume, plugin surface. Then we changed that instruction there. Let me stop that auto simulation. See, the size of the cell already is too big because it's growing indefinitely. Why cannot it increase this thing? Okay, let me go here to the and open the player again. I think I'm gonna have to close CompuCell again because.
Hold the bottom right corner of the bounding box of the tool.
But I am doing that. See,
Of
there
the,
is no
entire tool, not of player.
Here.
Yes.
Okay.
And why don't you try to arrange it so you don't have to keep scrolling, but keep everything on one screen?
Let's see if I can do that. No.
You have to be patient pulling the corner. It takes a second for it to pick up.
So I will get rid of this console here. Okay. So now the simulation is running, the cell is growing, but with straight, like a square. I mean, there is, since we have used that surface plugin, the surface plugin includes a constraint in the size of in the sizes of the cell. So we have chosen to put it like 20, and it cannot grow. There is a competition between the volume and the surface plugin. If you put a constraint too big in that in the surface plugin, it will prevent the cells to acquire a more rounded shape, because you are imposed that the surface has to have a certain amount of length. So the cell grows are squares. Okay, we can make a change in the code again to modify this behavior by allowing to the target surface to change according to the volume of the cell. I mean, the volume is growing. We know the volume is growing because we have this rate here that increase the target by 25 over 500. Okay, so let's do the following. Let's say that the target surface will grow with the volume as if the volume were a circle. I mean, I will define here a value of pi equals to 3.1446, something like that, for pi. And I will say that the target volume, copy, Ctrl V, the target surface will grow like 2 times pi times SQRT of cell dot target volume. Okay, I mean, you know, the surface in a 2D simulation is the perimeter of the cell. Okay, so I'm saying that here, that perimeter of the cell grows like 2 times pi times r of the circle, is the perimeter of the circumference. Right? So let's save it and start the simulation again. I have to get rid of this. Why is that? Every time the size is small. I have no idea why that happened. And every time I have to get rid of this console. Now something is back because I have the 25 to pi times pi target volume. What's going on? Let's see what's going on.
I think we need to take the plus sign out of the cell target surface line, so it's just the equals. That made it work on mine.
Oh yes, because thank you very much. Because I copy and paste the line to be fast. and the surface exploded. Yes, you're right. Well, it is 2 times pi times s squared. I have no idea what's going on. Okay, let's see if I can go to the code that I have here. I include this line and I run it. Everything is right. Something is wrong with his CompuCell here, I think. Sorry, guys, but I have to figure out what's going on here. Now everything went.
Gilberto, are there exercises that they can do that you can have them do while you're working?
Yeah, no, I am. Anyway, I think I'm gonna to
Could you
load
screen
mine
share?
here, and I
Could
will
you-
show the one I have done here in.
Is there an exercise they can upload? You have the code online?
Yes, yes, the exercise is in the students' materials.
But why don't you show them?
Is it, okay, let me see. You have to use a Jupyter notebook to upload it. Let me see, where is that folder?
Why don't you screen share the assignment? And then you can put that in the PowerPoint and screen share that, and then you can work on debugging while they work on the exercise.
Okay. Okay, the exercise would be to make that work, let's say.
No, but why don't you just show the slide with the exercise,
Okay,
the assignment? What is the assignment?
is 1.4.1. This one.
Okay, go back. Good, stop. So why don't you leave that on the screen share that, and then you can have people
Okay.
work on that while you work separately on your debugging.
Is it shared, isn't it? Now?
You can
Okay.
screen share just the PowerPoint.
Okay.
Screen share the PowerPoint presentation. No,
No,
just the
here.
PowerPoint. No, go to screen share in Zoom and just screen share the PowerPoint.
Okay, let me start this. Is that right now?
That's fine. Now you can work and
Okay.
people can work on this separately. So everybody should try to do the exercise on their own. And if they need help, please speak up. And I'm sure that Julio or Pedro will be glad to help you walk through it. Everything you need is in the Python cheat sheet and the CompuCell cheat sheet.
Okay, guys, did you manage to reproduce to do the exercise? I could not find the error in the NanoHub, but I will share my screen again here. And I will show you the simulation I have here in my computer. Okay, is it showing? Is James? Here, on the left side, I have the simulation I just made in NanoHub. And here I have the same simulation I did yesterday in my computer. The lines are completely equal. 25, 3, 23, 25 over 500, 2 pi's times blah, 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 is here. And here is the simulation running. I will start over, just to start with a single cell in the middle. And when I run, start to grow in a rounded shape. And if I do the same here with the NanoHub simulation, doesn't show anything. I don't know.
Close this, just close player and start again.
Okay, we'll go there to no ways. Launch to.
Gilberto, if you're having too much trouble with the NanoHub, just do it on your desktop.
Yes, I think just to check again. File, open the exercise 141 here from the one step, nothing there. So I will keep it with the in my desktop. Does it work for you guys?
Was anybody able to complete the exercise and get the growing mass of cells set up correctly at NanoHub? All right, so we got 1 yes, 2 yeses. Okay, so there must be something small that we're missing then.
Okay, I'm going to go with this simulation here, the presentation here, to the next step. Okay, now we have this cell growing. We need to start dividing it. one of the mechanisms for cell division in nature is mitosis. So we needed to figure out now what kind of biological event will trigger the cell division. Okay, there are many processes in nature, but and each one with many substeps. But in general, when the mitosis occur, the process is something like that. I mean, the cell starts to execute some movements, destroy the nucleus, it starts to and disentangle the DNA, and then it separates the DNA, rebuilds the nucleus, and the cell divides into parts, as you can see in that small movie there. Okay. So for us, as I said before, the simplest, since we don't have any internal structure in the cell yet, we are just increasing the cell to the double of the volume. When it reaches the double of the volume, we will divide the cell. So, when the cell divides, after the division, we have to analyze what's going on with both parts of the cell, okay? Because when there is a division, CompuCell has to create a new cell, a new object with a new ID, different from the other one to be identified. We can think about how do we transfer the characteristics of the parent cell to each one of the daughter cells. Okay, how would be the plane of the division? I mean, you can, if the cell is rounded like a sphere or a circle, it doesn't matter what the plane of division. But if you have a cell with any shape, elongated shape, where we are going to divide? Along the longest axis, along the minor axis, and so it's a kind of we have to decide. This decision is made on experimental observations, for example. Okay. Another thing is if the division is symmetrical. I mean, do the daughter cell have the same size? What kind of attributes, features each cell inherit? For example, are the target volume and surface of the daughters similar? Are the parent cell at the beginning of the initial state of the parent cell? I mean, if the parent cell starts with 25 and 20 as volume and surface, when after division, both cells will start with 25 and 20 as volume and surface for targets. Okay, so those are things we have to decide accordingly with the simulation we are trying to, with the experiment we are trying to reproduce. Okay? Now, if you imagine this volume represents the mass of the cell and the target surface represents the membrane, we will expect that when you divide, they have both half of those things, each one. Mm-hmm. So another thing we have to decide that if after the division, the both daughters have the same cell type, or one of them can be a different type of cell. For example, in a cancer simulation, for example, in a cancer experiment, we can say that one stem cell, where after division divides it to one stem cell, and they are non-stem cell. It's a choice we have to do based in the experiment, in observations. Okay? What will be the state of the cell after the division? I mean, both will start a new cell cycle from the first step of the cell cycle, or they are going to be in a state different of the initial one, a G1, G2, or S. Okay, it's always based in experiments. So to do these choices, CompuCell has a specific steppable called mitosis steppable. Okay, he is loaded beginning of when we do the project, and this mitosis steppable has lots of features that you can program, choose, and decide what kind of modifications the cell will have, the daughter cells will have after the division, and you can even say when the cell will divide, which cells will divide, which conditions for the cell divide, and so on. We were going to analyze my steppable right now. But before that, I have to say that the trigger for the division is something. It could be an internal effect, could be an external event in the microenvironment of the cell. It's up to the experiment you are trying to reproduce. Okay. This is the structure of the mitosis steppable. It's a class which goes in the steppable file. It's have this particular step function, which is very complex at the beginning. It can be even more complex if you decide. And it has basically three parts, let's say. At the beginning, we will build a dictionary to decide, to include, to list which cells are going to divide. That is the first yellow line in the right side. Then we establish the condition for the cell division. For example, if the cell volume has 50 voxels, then you include that cell in the list to divide. This is what this first block here is saying to you. And after that, we have a second part which choose what the plane of the division of the cell. If it is a random orientation, I mean the code chooses a random orientation, say we are going to divide in this direction, that's it. Or we can decide an axis based on a vector that will divide the cells in that particular orientation, or along the major axis, or along the minor axis, or any other condition you can implement by writing a Python function there. Okay. The second part of the steppable is the update attributes. I mean, after the division, how the cells are going to be. Okay. First thing, after division, we put the cell. We divided the cell, the parent cell, the cell which is going to be divided by 2. Okay, so just before the division, it gets half of the size. And then we clone all the attributes of this parent cell to the daughter cell. So at this particular step here, we are saying that the cell is exactly equal to the parent. Every single feature of the object cell parent and cell child will be the same, except their ID, because they must have to have something to identify them. Those is the cell ID. And finally, we can say, for example, if you wanted one of the cells to be different, another type of the cell. For example, in this particular red box here, I'm saying that if the cell type is 1, the parent cell is type 1, then the child cell type will be 2. Or on the contrary, if this cell parent is 2, the child will be 1. So after this if block here, we will have 2 different kind of cells, type of cells in the simulation every time. But it's a choice. We can say, and we can even change some attributes of the cell here. Okay, the easiest way is to say they are both equals. They just start growing, just like that. But we can start with two cell types at the beginning of the simulation and establish some rules for the division of both. So, here, if the cells are to divide when they reach doubling volume, I just have to include this line in the steppable step function, and to include in the list. Well, as we see in the first red boxes in the previous slide, okay? See, this is just a repetition of that previous slide to enforce what we are going to do. We make a list of the cells to divide. We iterate of the cells in that list and check if the cells have or not volume above 50. If they have volume above 50, they go to divide. They are appended to list to divide. Okay. After this is the volume condition, and finally the addition to the list to divide. Orientation is here. If
Gilberto, we're going to have to stop.
Why? It's too late.
Maybe present this, but we're going to have to continue tomorrow. Go over.
Yeah,
Okay, let's
give
finish
people-
then. I will just to say that we are going to choose here a division in a random orientation, and that after that we will have 2 equal cells with half of the volume at the division time. Okay, let me go quickly here. So before the mitosis, we have a single cell object like that. After the mitosis, we have 2 cells. Here I colored with different colors just to see that you really have 2 different cells here. Okay? And then the exercise. I will load the exercise then, and just to show you guys the exercise working. Let me open here. I'm gonna close the previous one. open the next one, which is 142, cell division. I'm going to show you the code. The construction of the code is in the exercise. So here we have the XML file with two kinds of cells now that I called stem cells and another kind of cells, okay? And the energies between them are the very same. Everything is equal for the same. And at the beginning, I start only with a single stem cell, just one cell at the beginning. Okay? In the steppable file, I have the same conditions as I have in the proliferate codes, 25 and 5 for volumes in lambda. The volume increases are in 25 by 100 now. It's a little bit faster than before. It's 1/4 of voxel per Monte Carlo step. Here is the division. When the cell volume is above 30, I divide it here. Orientation is random, the axis for division. And I will create two cells after the division. The two cells are different. So let's see I will close this old one. Opening player. It's very, very fast. I think let me try a little bit more slowly here, just to be able to watch. It's still very big, very fast. So you can play a little bit with the target volumes to see the speed of growth, let's say that. Now is a little bit more slow. I can visualize the cell border just to see the growth. And they grow until fill the space. Okay? So, this exercise is also in the demo. The exercise is in the student materials module, demos module 1.4. This is the 1.4.2. Okay. And if I don't have more time, I will end here, saying that we have this another one exercise that will be very interesting to do.
You can do it tomorrow, Gilberto.
So
Okay.
Gilberto, we'll have a little bit of time for this tomorrow. We do want to go ahead and move on to Q&A session, if you wouldn't mind giving me the screen share back.
Sorry, guys, I apologize for the problems with NanoHub, but I don't know. I have to figure out tonight what happened there to run there tomorrow. Thank you very much.
Sure. So I'll go ahead and put up just our closing slides here. So we do have about 15 minutes available for Q&A. Unfortunately, Julio had to run. He had some previous engagement. So we do still want to give you some time to at least voice questions. We'll do the best we can. But Julio will be back tomorrow, I believe, and he can maybe answer some of your questions in the morning. So thank you for those of you who have stuck it out this far and we're still around. Just a quick note, Our tentative schedule for tomorrow, we're going to have a first session on some CC3D demo applications, translating biology into models. Some of this may also be combined with the last couple of things we needed to cover in this module from today. Then we'll start talking about chemical fields and gradients, how to apply those to your models, as well as a little bit more about cell movement with applying forces externally and cell migration as well. We'll also have a midday hackathon prep session. I'll be emailing some of you tonight about maybe representing some of your hackathon presentations, so keep an eye on your inbox for that. And with that, I think we'll open the floor for Q&A. So if anybody had anything that they wanted to bring up or discuss before we break for today, feel free to put it in the chat or just speak up here now.
I have a question in this last exercise. I was able to include the class of mitosis, but I didn't find it. I don't know how to write the target volume for the cell when it is it must divide. You know, the target volume for dividing.
Mhm.
Sorry, I didn't hear you very well. There was a bad connect. Let me see about the check the sound. Say that again. So you're trying to say, how do you pick the target volume?
Yeah, I specified as it has in the code. There's for the cell itself, self list, if cell volume over 50, cell to divide.
Yes.
But when I run the code, doesn't divide.
I'm sorry you dropped out there.
What?
Sorry, there was an internet connection problem, so I didn't hear what you said.
Well, I set the volume at 50, but
Yes.
when it's well over 50 and it doesn't divide, is there maybe something I put in the wrong place?
Well, let's see, baby. Why don't you screen share to us and we can look at it together? Because I'm
Right.
sure if you're having problems, other people are having the same problem. That's why we have these question and answer sessions in the morning and the afternoon, because we're free to talk as we like. Okay, so let's see.
Let me just show the class. I don't know why this is here, but I think it's important. So, and I add the class of mitosis in the end.
Yes. Okay, so you're in the step function. You say how create a place to put your cell list. Yes. And then you say cell volume is greater than 50, cell to divide a pen cell. Yes. Then you say for cells to divide, fine, self-divide random, yes. And then you give the parent half the area and the daughter half the area. But scroll down. Let's see the end. Okay, and you're changing the cell type. Fine. Okay, so this is the default. And now what happens when you run it?
Save everything. Save everything. Victor.
All right.
You have to save the other files.
Yes, update
All right.
installed when you do cell.
Clicking the double discs. Double, yeah,
right.
solve everything.
All right. Let's see. Oh, I forgot to run. Oh, there it is. So I didn't save the other files as well. That's the problem.
Yeah,
Always use the save all button when you save your file.
All right. Thanks.
No worries, that's a common mistake.
No, there is no, you shouldn't need to use the C++ ever inside of CompuCell. It's true that the error messages will give you the list, sometimes when you go through the list of errors, you have to find where your line is. But it will always point you either to a Python or an XML line.
Okay,
So
thank you
Vitor,
very
do
much. Oh, sorry. Go ahead.
I was just going to ask Vitor if you mind if I stop your screen share here.
All right. Sorry, I didn't do it myself.
No problem.
Go ahead. Rosie?
Oh, yes, thank you. I was gonna ask, I noticed that also in like the Twedit page with where you can see all the files, there's a little thing in the top left corner where you can look up components to add for the Python or the XML files. And there's also a thing for C++. So I didn't know if there was any extra information, I guess that could be code that the user could code through that, or is that just something that runs in the background?
No, so I guess the question is, your question is, can you write C++ extensions? And the answer is absolutely, you can write C++ extensions to CompuCell and to Twedit. And there is a support for doing that. And so if one is ambitious and you want to write things that run extremely fast, or to provide functionalities that don't exist in CompuCell now, it's definitely possible to do C++ extensions. But the point of CompuCell is written to try to minimize the amount of times that you'll have to do that. So if I look at the examples that we've written in the past 15 years using CompuCell published, none of those had, well, it's not true, 1 out of 45 papers used a C++ extension. Everything else was using existing core CompuCell. Now, there certainly are places where it would be nice to do C++ extensions. If you wanted to do something where you have explicit fibers and you want the cells to move along fibers in a particular way, for example, that's the kind of place where you probably would write a C++ code extension to do it. And if you're interested, I don't know if we're going to be able to cover that in this week because it's a lot of material to cover already in a week. But we definitely can show you how to do that if you're interested, if there's a specific application interest.
Okay,
TJ.
thank you so much. I saw the thing in the chat too.
I'm sorry not to be able to just show you how to do it, but definitely it's possible.
Thank you so much. Thank you. I really appreciate the information.
Any other comments that we should address?
We have a question in the chat from Issy. Could you please explain what is included within axes equals self.moment of inertia plugin? Is it the vector direction?
Yeah, so I wanted to be able to update the length of my cells as a function of like the chemical gradients or some other environmental factors.
Yep. So you can adjust target length for each cell individually, yes.
You mean the actual target length parameter?
So when you define the target length in the XML, it generates a global for that. But you can update so that each cell has a unique as a cell-specific target length.
Okay, because when you do like self dot target length, it doesn't have anything in it. So how do you access it in the Python script?
Okay, so that one I would have to look up in the manual because it's not a function I use very often. So in general, Python CompuCell gives you a choice where you could either specify values in the XML, which are typically for all cells or for all cells of a given type, or you could specify the values in the Python which is cell specific. And TJ, you know, if you're here still, do you know the answer for this specific question for the target length? Because as I say, that's not a plugin I use very often, so I can't answer that question.
So for which part of it again? I'm sorry. I was looking at the question about the moment of inertia.
It's for target length. So you can introduce it in the XML, but you can't access it in the Python as cell.target length.
Let me check. I'm pretty sure you can. Sorry, it's been a minute as well for me since I've used that one. It is settable. Yes, I've written some demos that show how to change it interactively. And it should be in the quick reference guide. I believe it's just target length is the name of the property.
Okay, I was having some errors when I ran it, but I'll try it again. And I'll
Well,
come back.
again, if you'd like to screen share.
Are you using this piece of code here that I put in the chat? I see.
Oh no, I'm not.
This is the code that appears when you use to edit to implement.
Oh, cool. And is that 2020 the target length and the lambda length?
Yes.
Oh, awesome. Thank you so much.
I'm sorry about that one. Some of these things I know off the top of my head, some of them I have to look up. That one I have to look up. I generally, when I want to build elongated cells, I usually use compartmental cells and make the cell out of a bunch of subcomponents. That gives you a little about the shape.
Yeah, that was definitely going to be a future question of mine because I get a lot of fragmentation if I try to get them more closer to the elongation I'm seeing in my experiments.
Yeah, 2:1 is about the most you can do using that length constraint.
Yeah.
If you
Okay,
want
so you'd
something-
recommend compartments.
something with like bacteria where you have long elongated cells, your best bet is to do what Julia will teach us on Thursday and Friday, which is to use compartmental cells with links between the compartments.
Yeah,
That's
okay.
That was a method that was originally developed by Andreas Deutsch in Dresden for simulating bacterial movement, and it works pretty well.
Okay,
But
awesome.
It's a little bit more advanced than where we are now, but I'm happy to sit with you and do it. It's not hard to implement, just that we haven't gotten to it yet.
Yeah, that would be awesome. Thank you.
Okay, thank you for being patient. Okay, any other questions? I guess no question too large or too small or too different.
I have a comment, but yeah, I sent a proposal to Hayden. Probably I would like to develop a project for the hackathon. I am
Great.
Norma, so I don't know if you receive it, the proposal, Hayden, via email.
When did you send it?
Today in the morning.
Today? Yeah, I'm sure I got it. I'll be checking my email inbox after this to get all that organized.
Okay, thank you so much.
Did you have a specific question about it now, or did you just want to check that I got your email?
Yeah, I just want to check if you received my email. So, yeah,
Okay.
we'll talk later.
Yeah, I'll if I don't have something from you, I'll let you know.
Okay, thank you.
Okay, anything else people want to bring up? You've been very patient today. We appreciate it.
I have, oh, sorry, you go.
I was asking about that update attributes function. I didn't quite follow where that comes in and where it's called from. Is it automatically called by the division, cell division?
Yeah.
function?
As soon as whenever a cell is divided, it calls update attributes.
Okay, so the module or the plugin provides that function, but then you just you have to provide the internals of it to say how the update works. Okay, it's like a callback.
Right, exactly. The main thing that's provided is that clone attributes, which is pretty powerful.
So that you set up you change the attributes on one cell, and then the other cell just gets the same attributes.
If you do it, yes.
If you,
I mean, typically you give half of the area of the volume of the parent cell to the daughter, and then you clone it. If you've got surface constraint, you might update the surface constraint first too. And you have there are a lot of features which we don't use that often, which allow you to select what is cloned. You can clone pieces of things, and there are one or two things that still don't clone. I think links don't clone. Everything else does, but the thing that's tricky about it is even user-defined things clone. So if you created a dictionary entry, that will clone properly. That's actually one of the nice things about Python is that Python introspection lets you do that. Deep copy uses Python deep copy.
So what does that division function provide other than what you put in the update function? Is it just that it creates like a second handle for a second?
Well,
cell?
it reassigns the VOC. It creates a new cell. It defines a relationship between the two cells, the existing cell and the new cell as cell and daughter.
Okay.
It defines, it reassigns the voxels that were in the parent cell to belong to the new two child cells.
I see.
And it does that according to the rules that you specify.
Okay, so it kind of physically splits it, but then you just have to provide the behavior, basically, by changing the target values and such.
Right. Again, that clone attribute function is the big one. And so the calling of that clone parent to child is the main.
Okay. I typically think of clone as a kind of copy, but it's only copying the attributes. The cell already exists. You call clone to copy the attributes over from one to the other.
That's right.
Okay, that makes sense.
It's computational clone rather than biological. Okay, good point. Good. Other comments today? It's been a long day, I think.
Yeah, I had another question, but I'm happy to wait till tomorrow.
Oh, that's fine.
So I'm looking at having some stem cells that are immobile. And I had them fixed, but because they need to produce new cells, you can't just fix them. And I tried dividing along the same vector direction and having a wall that they sit against that they have a low energy for, just to try to get them to stay in place. I find that eventually they, especially if I have more than one layer of stem cells, they eventually get pushed away and just get carried away with all their daughter cells. Do you know any ways to make cells just immobile?
Well, so the only way to really make a cell absolutely immobile is to freeze it, and then it won't divide.
Yeah.
So you are a bit stuck there. Yeah. One thing to do would be to create a cell type that you think of ways to cheat. You could create a cell type that's immobile, a frozen cell type. You could change the cell to a non-frozen cell type, do the division, and then change it back.
Oh, okay.
But typically, I mean, biologically, nothing is ever totally immobile. So it's not really a very biological thing to do, but it's convenient. I mean, the other thing to do, which I tend to do, is if you really want the cell to behave like a cell, but not be frozen, absolutely frozen, then if you make the lambda volume, the volume constraint, very, very large, then that cell will prevent the cell from moving. Not 100%, but effectively keep it from moving. But that's one where I'd love to sit down with you, look at your code, play with it with you, and try to solve that problem. I'm not sure I can do it.
Great. That would be awesome. Thank you.
I'd be happy to spend an hour going over it.
Awesome. Thank you.
Well, I'm glad that there are questions. I mean, I understand it's a long day, but I think it's great that people have been working on problems and have good questions to ask. And again, we do our best to answer them, but sometimes we don't have immediate answers. Any other questions? No, well then I'd like to thank our speakers for today. I hope to see you tomorrow morning. If you have questions beforehand, we'll be here around 9:40 and have 15-20 minutes for questions before we get started tomorrow. Otherwise, thank you very much for coming, and I look forward to working with you for the rest of the week.
Yep. Thank you, everybody.
For those of you in bad time zones, we really appreciate your being here.
TJ, are you able to send me that